Now we have a very interesting problem. We have the circle. Actually, this one's solid circle, so to speak. It's all filled in because it's x squared plus y squared less than or equal to 1. It's all the points inside the interior of that circle of radius 1, including the edge. And the cross sections are isosceles right triangles perpendicular to the y-axis with one leg a chord of the disk. Okay, so that's what they look like, and I drew in a sample one in my usual mauve color, so you can kind of tell that. That's my sample triangle. Bear with the picture. The height and the base are supposed to be the same size, and of course its area is 1/2 the base times the height. And say for the ith slice, that's the ith slice we have here, we'll call this point x sub I, y sub I, and we have the relation x sub I equals the square root of 1 minus y sub I squared because it's on the circle. Now, this length from here to here is xi, but from here to here is 2 times xi. And remember, even though my picture doesn't make it look like it, this is an isosceles, so this is also 2 times x sub I. So for the ith slice, we've got the volume of that slice, 2xi times 2yi over 2xi times 2xi over 2. That's 1/2 the base times the height, times the thickness of the slice, which is a little delta yi, a little amount of change in the y direction. Hopefully you can see that part okay. So this 2 cancels with one of these, but we still have the other one. So we get that 2, the one that didn't cancel, times xi times xi, that's xi squared, where xi is the square root of 1 minus y squared. You know, I must have this as a function of y because my delta is a y value, right? The delta is a certain small change in y, so I need to have y be my variable of choice. So I replace the xi squared with square root of 1 minus y sub I squared. And of course that simplifies as just 1 minus y sub I squared. And so that is the approximate volume of a slice. And if I added all those up, the volume of the entire figure is approximately equal to this. And of course I want to take the limit of that as the maximum of those delta y's approaches 0, and that's kind of an obvious choice there. Although I have to say I isn't going from 1 to 2. Oh my. 1 to n there, and of course n must be infinite if we're letting the maximum of those goes to 0. So again, we're doing the usual thing, adding up an infinite number of infinitely small things. So our limits of integration, if you go back and look at the picture, I didn't draw it, but remember it's a unit circle, so y goes from here at -1 up to here at +1. And so that's kind of an obvious part. From the Riemannian sum, the 2, I guess we could factor that out. I didn't. Times 1 minus y squared dy, that's the thickness represented. And so then we just need to evaluate that integral, which is 2y minus 2y cubed over 3 between -1 and 1. So that's 2 minus 2/3 minus -2 minus -2/3, so plus 2/3. And so what we wind up with is this 2 plus this 2 gives us 4, which is 12/3, and this minus 2/3 and this minus 2/3. 12/3 minus 4/3 gives us 8/3. So the volume of this particular figure is 8/3 units, whatever the unit may be.